Right. Hello, everyone. I think we can get started. It's 10 o'clock Central Time. So welcome, everyone. Thanks for participating in our digital pathology webinar series session today. I'm very excited for this session, which is specifically focusing on overview of machine learning in digital pathology research settings. So we will begin by having Dr. Brittany Duggar, who is Assistant Professor of Pathology and Laboratory Medicine, as well as the Neuropathology Co-Core Leader at UC Davis's ADRC, and UC Davis Women in Medical and Health Science Department Liaison, and co-leader of the UC Davis School of Medicine Machine Learning Working Group, present on this topic. Following Dr. Duggar's presentation on the overview of machine learning in digital pathology research settings, we will then move on to have a live Q&A session with all of our panelists. So Dr. Duggar, in addition to Dr. Thomas Pearce, MD, PhD, Assistant Professor of Pathology and ADRC Neuropathology Core Leader at University of Pittsburgh. We also have Lee Cooper, PhD, who is Associate Professor of Pathology and Director of the Center for Computational Imaging and Signal Analytics in Medicine at Northwestern University. Dr. Sandra Camelo-Piragua, Clinical Associate Professor, Neuropathology Fellowship Director at University of Michigan, and David Gutman, MD, PhD, Associate Professor of Biomedical Informatics at Emory University. So take it away, Dr. Duggar.
Thank you immensely, Dr. Flanagan. And thank you all, everyone, for attending today. I know there's many things that people can go to, especially in this wonderful virtual environment. So really appreciate you stopping by. So I'm Dr. Brittany Duggar, and I'm going to give a short presentation, 30 minutes tops, just to kind of set the stage for a lot of this stuff. And again, let me advance my slides here any day now. There we go. We have these great panelists today. So even though I am giving this overview presentation, we have a great amount of expertise with these wonderful people, and hopefully you can match, this is a nice little trick this morning, match the photo to the name. Yay, memory game, early this morning. So again, and a special thank you also to NACC, the National Alzheimer's Coordinating Center, for helping coordinate these wonderful webinar series, which have been going on now for, I think, over a year. So it's just been very great to have that help. So thank you, persons at NACC, especially Hannah, you've been fantastic coordinating that. So to get started a little bit, for those that might not be familiar, we're going to be focusing on neuropath today, specifically related to Alzheimer's disease and related dementias. And so here's just a great figure from a recent review that was just out on the 6th, I believe. Yay. So kudos to the med student, Mustafa Shakira, who helped with this, and Dr. Luco, who actually made this figure. So this kind of summarizes what we try to do in our Alzheimer's disease centers. We try to capture this neuropathology landscape of the who and the what, which is that type of the pathologies, and the where, the anatomic location, and the when. So when throughout the course of the disease, which is we get great clinical data, and then when the person passes away, we had that great privilege of analyzing their brain. And this can then lead to the why and the how, because we want to cure these diseases. We want to prevent these diseases. So this, that whole kind of concept, the who, what, where, when, why, and how. And so from a neuropathology standpoint, we have many ways of obtaining neuropathology data. We have our kind of established semi-quantitative scores, which we use to fill out our National Alzheimer's Coordinating Center forms. We can do positive pixel counts where we can trace an area. And there was a great presentations before on this with the Perio software, as well as with QPath. We can do intensive stereology, or we can just basically do counts. These are some different ways that we obtain pathology data. But the problem with this is there's limitations with these methods. They require a certain level of expertise. There can be inter and intra rater reliability issues, can be quite time consuming. You can have limited statistical power to evaluate associations. So think none, mild, moderate, severe. You only have those categories. Everything can asymptote off at severe. So how are you making correlations? And then we run brain banks, and these brain banks have been in existence for decades at some point. I think with our Alzheimer's Disease Research Center, we're going on 30 years. So it's amazing to think of staining over time and how that can change. So these tentorial properties of the tissue and how can we adjust for that. And so we are in this age of machine learning, which is great. I can take a photo of myself, and as a disclaimer, I have nothing to disclose. I'm going to try not to endorse anything, and anything said here is not reflected on University of California, Davis or NACC. These are kind of my own little things. Sorry, just making sure we state that disclaimer. So with Google Arts and Culture, and this is a really fun app, I can take a photo of myself, and it goes against a database of all these famous paintings and says what painting that I look most like. And so here I'm 65% compatible with the portrait of a young woman, but then also with that same photo, I'm 67% compatible with an old woman. So very, very interesting, right? But my most favorite, even though it's the least compatible, is 62% portrait of a lady. So very interesting aspect where I take a photo of myself, right? And then it goes against an archive of what do I look best? And there's these three possibilities that are within a couple of percentage points of each other. So how does that fall? So the question then we have is, can we use this technology to help better our practice? And this just to set the stage of how this compares to IHC's immunohistochemistry, just as a comparison, right? I'm not trying to, highlight anything more. As you see all these papers that are published, if I search on PubMed, Alzheimer's disease plus immunohistochemistry, you get a ton of papers. And then here you have this start to rise of Alzheimer's disease and machine learning right around 2009. There are a couple papers before that. And a lot of these papers in the early ages of this were focused on in vivo imaging, specifically MRI, object detection. Okay, but then it wasn't until 2019 where myself, with the great help of Dr. Michael Kaiser at UCSF and his team, where we put out a pipeline for image classification with Alzheimer's disease, but then also Dr. John Crairy's group did as well. So we kind of have, he focused on tangles, he's a Taoist, even though I'm kind of a Taoist too, but I focused on amyloid beta. Plaques are a lot bigger, so we kind of divide and conquer. So those are kind of the first two. Doesn't mean we're the only ones, and I just wanted to highlight this in case anyone's interested. It's always good to have that baseline literature of what's going on. So these are a ton of other papers. So you see our papers here. There's that follow-up paper by Dr. Gutman's group, who's on the call. And there's also a lot from Mayo Clinic that's coming out, as well as UT Southwestern. So if you know of another paper, let us know. Just wanted to get some of these out there so you can kind of see that a lot of people are picking up on machine learning, utilizing our wonderful digital slide archives. And so I'm using these terms, right? I'm using machine learning, but what does it actually mean? How is it different than artificial intelligence? How is it different than deep learning of neural networks? So these are all kind of terms that people use, and I just wanted to show you how they're nested. And I adapted this from a Coursera course, which is great if you want to dive a little bit deeper into this. It's called AI for Everyone. And so with artificial intelligence, the definition is basically the capability for machines to imitate intelligent human behavior, the overall definition. So you think about when people are putting out papers and might be using the term AI, it technically probably isn't AI, even though it's a very sexy term, if I want to say that on a lovely Monday morning. What they're really probably using is machine learning, which is the application of AI that allows computer systems to automatically learn from experience without explicit programming. Okay, so that's kind of just the difference between those terms. And then within that nested variable, again, is the deep learning aspect, which these are types of machine learning methods. So deep learning and neural networks. And again, just giving you an overview, and we have the panel here that can answer additional questions if you need. So those are some terms and definitions. And then another important thing to note is a lot of people want to use machine learning, but we have to take a step back and realize the cans and the can'ts. So with machine learning, it tends to work poorly, and notice I'm being very lenient on that learn, is when it's trying to learn complex concepts from a small amount of data. So I gave some examples here, or asked to perform on new types of data. So I gave an example here of, okay, you give a couple different examples of tauopathies. You give it some R-tag, you give it a pre-tangle, you give it a full-blown tangle, you give it a ghost tangle, whatever. And then, hey, can you identify all the different types of tau pathologies? Machine learning will probably work poorly on that. Or another way you could think of is when you're training data. So the brain has a lot of different neuroanatomic areas. So cerebellum looks a lot different than the putamen, which looks a lot different than cortex. So if you're training data on a certain type of location, so say the cortex, and then all of a sudden you present to it cerebellum, the machine learning algorithm has never seen that. So it might freak out. I don't know the technical term for that, but just to get that point across. When machine learning, it tends to work well when it's learning a simple concept or a task. And a task I operationalize into something a human can do in 2 to 3 seconds. And then have a lot of diverse, clean data. And I'm going to emphasize that in a couple other slides what that means. And so, for example, a simple task could be, is this an amyloid plaque? Yes or no? So hopefully that helps if people are trying to delve into this and what it can and can't do. And so there's also different types of machine learning. A lot of those papers that I showed you, a lot of us in the pathology realm are delving into supervised learning because this is task driven, or you have a set of annotated data from an expert. But there's also unsupervised. So this is more of that cluster analysis that people will do. They'll put in a whole bunch of variables. Hey, can the machine find a pattern? And then last but not least is reinforcement, which is a combination of supervised and unsupervised. With reinforcement, a lot of self-driving car applications are using reinforcement learning. So hopefully that helps kind of define those 3 types of machine learning that are being used. And so with supervised machine learning, and again, I'm only presenting for about 20 minutes, so just bear with me here just to give an overview. Basically, you need to label lots of data. So here I am as an expert trying to classify things into different amyloid deposition types. Is it a dense core plaque? Is it a diffuse plaque? Or is it cerebral amyloid angiopathy? So I go through and I try to label all this. And then we get these images, and hopefully you can appreciate here is we have to divide them into 3 groups: a training, a validation, and test set. That's typical of machine learning for supervised. But then you also can have what's called class imbalance. And this is very important to note because certain things are just going to be rare. So think about diffuse plaques, and we see diffuse plaques. They're a lot more abundant typically than cerebral amyloid angiopathy. In a typical case, you could sit here and partition and be like, oh, well, this is this type of case, so it's going to have more CAA. But for the most, you need to really understand that because that's also going to be driving what type of metrics you're going to be using to evaluate how well your machine learning algorithm is performing. And so with that, then we kind of have, this is a typical convolutional neural network. I know this is a lot of letters and numbers early in the morning, but I'll break this down in the next slide. And so you have a multi-classification labeling system, and then you basically, the machine learns from the expert, you train it, then you validate it, then you test it. And you could even have further testing with holdout sets or using different types of data, things for generalizability. So those layers, so you saw how there's those different colored boxes. Each one of those represents a layer. And I think this is, if you're again, so there's the Coursera course by Andrew Nye. But if you're more interested in just reading a good book about it, deep learning is a really good Bible. I don't want to be too religious, but just to kind of get that across for getting up on deep learning, machine learning. And so say here you have a wonderful picture of a person. And so you have these visible layers, it's your input pixels of all these different colors. But then with each one of those convolutional layers, you basically are looking at different aspects, because with a computer, they kind of think in a binary way, like, is it there, is it not? So you have a whole bunch of zeros and ones. And so you break all this stuff down as, okay, does this pixel have an edge or not? And then you move on to the next layer. Okay, corners and contours. Does it have a corner contour? Yes or no? Object parts. And so you break it down into all these different things. And then you have your output, which is the object identified. Granted, there's a whole other stuff that goes into this, but just again, trying to break machine learning down, supervised machine learning down to its simplest concepts. And so again, to reiterate, if you want to start looking at machine learning in your practice, you need to have some brainstorming framework. And I can't emphasize this enough. And I'm very, very blessed to have so many great collaborators and colleagues that have helped me, because I'm more on the domain expert side. So I'm more on the neuropathology side, even though I'm here talking to you about machine learning. A lot of stuff I learned from my colleagues. So you have David Gutman on the line, who's been great. I also have Dr. Michael Kaiser from UCSF, who's helped me, and Dr. Chan down at UCI. So I have a lot of great people that I can go to be like, okay, what does this mean? And they can help tell what machine learning can do. And what we really want to see is that intersection, because you can have a great idea like, oh, I'm an expert, I want to solve this. I want to have the diagnosis for Alzheimer's disease. Machine learner person's going to be like, hey, wait a second, we need to break that down into its simplest components. So we really want that intersection. And so with that, we have to think about automating tasks rather than jobs. So again, a task is something a human can do in 2 to 3 seconds, rather than a job. Like diagnosing Alzheimer's disease, the whole shebang is a job, right? And that's composed of a lot of small tasks. And then as a domain expert, we really need to communicate what are the main pain points for our healthcare domain. As we know in research, a lot of times we'll do stuff because it is really, really cool, but we really have to think what's our biggest bang for our buck, or ROI, which is return on investment, to really get the ball rolling on this. And so I presented that small Venn diagram, but let's take a step back even further, that we really need a very diverse dialogue when we're dealing with these machine learning process to have the biggest impact. And hopefully you see there's a lot of different domains and levels of expertise that are listed on this slide. So here on this end, you have statisticians, informaticians, computer engineers. It's really good to build all that into your team, because it's really going to help you in the long run get that biggest bang. And here you have on this side a lot of that domain expertise. And the big thing here too, because we all have really busy lives, and it's really, really good to delegate and to train the next generation. It's really good to have those connectors be students, staff, junior specialists, and they're really the ones that are in the trenches that can really help. And that's what's worked for us. And that's, again, just trying to say from our own experiences. And so with that, so kind of presenting now, moving down a little bit further, kind of the stepwise consideration when you're building these machine learning models. So step one is trying to evaluate what type of data you got and accessibility and its quality. Is it validated, or are you just taking something, say, from electronic medical records and hoping for the best? What's the completeness? What's the distribution of those classes? Like I showed you about the diffuse, the core, and the CAA. How is that divided? Do you have imbalance? How generalizable? Many of us are in academic healthcare centers. And with academic healthcare centers, you're going to have certain types of persons that are going to visit your center. So you're going to have some bias in your data. So it's really important to think about, or even with an Alzheimer's disease center, you have cohort inclusion and exclusion criteria. So how generalizable, again, are your data points? So that whole concept of real world versus research. So then with that, you evaluate your data. Then you want to validate and identify optimal AI ML models. There's a lot of stuff out there, and to really think about this. And again, this is where those experts and that diverse team come into play. And especially you have to take a step back and think about determining your goals. So what error metric? So what are you trying to achieve? Do you need to have 90% accuracy, precision? You have to think of all this. Are your classes imbalanced? So asking some of these questions. So do that, and then you assess the model generalizability. And there's a whole bunch of things here, even opening up that black box. A lot of times you'll just see a graph, but what is the machine looking at, and verifying that performance with real world data. So again, there's a lot of steps in here, but just to try to synthesize this. And all this is located in a great review by one of my colleagues, Dr. Rashidi, who now moved to Cleveland Clinic, is that he used to be at UC Davis. And another way to present this, and a nod to the radiology community who is actually published on this too, is even when you're reading a paper on machine learning, what should you look for? And this is just, again, a great checklist, kind of very similar to what you saw in that previous slide. Is, are there 3 imaging sets? Is there an external test set? Have multi-vendor images? So in digital pathology, If you remember some of the previous webinars, we did talk about different slide scanners. So those are the multi-vendor images. So has it been validated and used that algorithm across those different standpoints? And I can go down the list and read this to you. But again, just a great resource to try to understand when you're reading papers or want to publish, you know, what should you include? And so this is kind of what our workflow was when we first published. So when we were establishing a working end-to-end pipeline. Okay, so what's our starting material? What do we want to end with? So first off, we scan the slides. And we started with one anatomic areal, the temporal cortex, and stained with one stain, 4G8, which is for amyloid beta. Then because we want to decrease a lot of the variability, again, we've been a brain bank for X amount of years, there's going to be tinctorial property differences. So we did a color normalization, and this was mainly for a lot of the annotators because we want to try to make sure that we keep things as constant as possible, not so much for the machine learning algorithm. And then even with slides, those files can be huge, like 1 gigabyte. So how can we partition that down into its simplest component to help things run better? So we decided to do a tile level segmentation and pull out objects of interest. So get rid of all that negative space to have smaller file sizes, which means faster run times. And then put those into an annotation platform. Notice on this whole slide, I haven't even talked about machine learning yet and running those algorithms. Because again, understanding that pipeline of how are you going to process that data to get it to its simplest components, as well as understand some of those bottlenecks. So one of the big bottleneck could be annotation. So one of the things we came up with, so typical annotation, somebody could, you know, you get a file, you open that file, you mark it all up, you close it down, and then you can sling it to your collaborator. Multiply that by hundreds of images, by thousands of images. That's a lot of time. How can we speed that up? So this was very great to, again, have that diverse team where we talked about everything. We actually deployed an annotation platform using AWS. This is an Elastic Beanstalk website. So just think of when you're looking on Amazon or Netflix and you can flick through things really, really quickly to make a choice, kind of thinking about that same concept. And so here we can show just single images, making sure things go very quickly. Even from a categorizations, I could come over here and click these categories every time, but that's going to take time. What if I have keyboard shortcuts? So I can make it go even faster to collect data quicker. And so even on top of that, we also wanted to have motivational things. So coming from that psychological standpoint of, okay, could this be as popular as Words with Friends? That would be awesome, right? How do we motivate? So we had a little gamified theory here. We have a little crown. Oh, you're on level 8. You annotated this many things. So pretty cool. And with this, I was able to annotate about 2,000 images an hour. So when you think about that throughput, very, very nice throughput. So you can hurry up and do that. And then with this, here's our performance metrics. And so we have the receiver operating characteristic, and to remind, because I know it can be early for some people, the receiver operating is basically true positive versus false positive rate. And you have this trade-off of which way you're going to go. You're pretty much never going to get it 100%, but how close can you get? And then you also have your precision recall curve. This is a good metric for imbalanced data, right? Because you want to factor in that recall. It's not just the fact that, oh, look, I did a whole bunch of great stuff, but I only had 7 things that I looked at. So again, nice little definitions down here for those where it's still early, you're drinking your coffee. But for me as an expert in neuropathology, I see these curves and I'm like, that's great, but what is the machine looking at? That's what we kept asking ourselves. Like, I want to see how the machine is making its decisions. And so how can we interpret this? And so there's different ways that we kind of did this. We did heat maps, because in neuropathology, certain pathologies are going to have certain anatomic locations. So why not do a heat map to see, does the location match where it should go? Okay, so here, CAA mainly in the leptomeninges kind of here, diffuse plaques are diffused all over, makes sense. Other things we did just to kind of confirm was we did the gradient weighted class activation mapping, which is basically what the machine is looking at. So say you walk into a room, lecture hall, are you going to look to the ceiling for students? Not really. You're going to look where the desks are, right? So this kind of whole concept of all this white denotation here is what is the machine looking at on that image when it's making a decision? So here with the core plaque, it's mainly focused on the core. With diffuse, you can see it pans around a little bit, focusing on the diffuse, but it also glances over here at the core just to make sure. And then with CAA, which is not at all on the image, it still looks around a whole bunch, but it really doesn't focus on the core. So just again, interpretability. Other things you can do is you can do a feature occlusion. So just take out a couple pixels, see what happens to your confidence scale. And hopefully you can see if I remove a core on a core plaque or a dense core plaque, the confidence interval changes completely. Makes sense. Again, that interpretability for understanding how that machine is thinking. And so even though we published that paper, right, the whole slide images were from one source, one stain, one anatomic area annotated by one expert. And it was only for select neuropathologies. So there's a lot of limitations, but at the same time, we did the pipeline. So what do you got to do in research? It's not just search, it's research. You got to redo it. So can other do these same methods? And yes, they can. So they were able to, and Dr. Gutman can talk more to this, paired with him way back when. It feels like decades, Dr. Gutman, but had a great student, JC Fiscara, who basically tried our same methods on the Emory database and got similar results, but he took it a step further and tried to do subtyping. So that whole neuropathologic landscape of, okay, what does Alzheimer's disease with TDP look like? Alzheimer's disease with blue dye, how do their plaques look like? So fast way to do this. And I think this whole project from the time we initially met Dr. Gutman to when we published it was little under a year. So very, very quickly did we develop this, which was really cool. Other things to think about, right? So only one expert. I only have one opinion, right? As much as I want to say I'm as objective as I can be, there is some subjective nature into what we do examining neuropathology. So what of inter and intra-rater reliability? So it's that whole, we talk about ground truth. And this is being led. So again, hopefully some familiar faces. You can see Dr. Flanagan's here, Dr. Koffler, Dr. White. We even reached across the pond with Dr. McAleese and Dr. Boyles. And then we also recruited some novices. So this is a great way to train the next generation as well. So think about how we can get people earlier in their career interested in pathology. We could have that platform, send it out, see what they say. So we did whole slide images from 3 different brain banks, and then experts annotated these things. And again, great partnership with University of California, San Francisco with Dr. Mike Kaiser. And this work is being led by Dan Wong, who's now, I believe, a doctor now. So congrats, Dr. Wong. And surprise, surprise, there was a lot of disagreement, but that's okay. The question is, how do we factor that into our model systems? Because this is going to happen time and time again. There's been even things of, hence in the medical field, always get a second opinion, right? So here's just some Venn diagrams. This paper currently is located on bioRxiv, and you can see how as persons, so basically this is one person agreed that this was of that classification, 2 people, 3 people, 4 people, 5 people. So hopefully you can see as the agreement gets higher, the image gets more defined. Makes sense, right? But how do we test that? So one of the things we started to do is what's called ensemble modeling. But what we also did was we threw in, I call this the fake news experiment, because you also want to understand is it's not just anything that you throw into the model. Can the model actually discern when something's not an expert annotation? So we actually devised random labels here and threw this into our model system. And hopefully you can see here, this is a graph on the right here, that the absolute value of our precision recall didn't change by much when we did this fake news experiment. So again, these are just different ways that I'm going over that when you're doing machine learning model systems, how do you test its robustness? How do you test its generalizability? Other things we can also do is, you saw how we were identifying the plaques. We can also add in other tasks. So this is great work done here at UC Davis, led by Jeff Lay, and great partnerships again with the computer engineering department. So a lot of students in computer engineering can be looking for projects. We have data, it's great pairing. And so they started gray matter, white matter segmentation to add into that pipeline. And they were actually testing, Jeff, Wenda, and Colin were actually testing all these different architectures. So all these UNet, FCN, ResPat, these are all just different types of machine learning architectures and what performs the best. So again, not just going like, oh, I'm going to use this, let's test it. Just like with statistics, you have different model systems, same thing with machine learning. And so I covered a lot today, and I want to make sure that we have enough time for the panelists because there's a great plethora of expertise here on the line. So we define machine learning, how we created scalable workflows, developing and then validating. And then I'll leave this slide up here for a little bit as we change over to the panelists, because these, again, I just wanted to summarize some of these resources. Feel free to take a screenshot if you want, because it's sometimes hard, I know, with the long URLs for that. But AI for Everyone, this is a great Coursera course. We published a while back, this is the Digital Pathology Working Group through the Alzheimer's Disease Centers about digital side scanners and associated infrastructure. And Hannah mentioned about, we've had previous webinars. So if this is your first one attended, welcome. If it's a second, third, fourth, we're very glad that you're here again. We put all our stuff up on YouTube. Also other great resources, College of American Pathologists. Actually, I have a nice topic center on digital pathology, and another one is Digital Path Association. So just some nice resources if you're interested in just kind of clicking around and learning more. And with that, we can change over, and thank you again for your attendance. I'll stop sharing. I'm going to have a drink of water.
Thank you so much, Dr. Duggar. That was awesome. So much information and a really nice walkthrough of some of the things you've been working on and some of the applications for machine learning and neuropathology research. I just wanted to also say, if everybody could please just enter any questions that they have into the Q&A box, then we can start with the live Q&A session. And it looks like a first question here. I am interested in applying ML unsupervised learning, I suppose, to query how the human neuropathologist defines a structure versus how the machine classifies it. For example, as a human, I often struggle with a darkly stained small plaque, quote, compact, if you will, although the historical classification has been diffuse versus cord. This isn't a binary system. How can we effectively use ML to help us refine diagnostic criteria?
So in terms of whether or not this is a machine learning question versus a intra-rater question, I mean, some of the stuff Brittany was showing, although my experience has been no one ever really wants to do this, is basically creating a photo gallery and having 5 or 7 or 9 or whatever the magical number of neuropathologists needed. And you just have to basically show them lots of examples of this gradation. And that's kind of one of the biggest problems with all of this stuff. You know, almost nothing's really binary, and everyone even has their own, call it ROC curve, where Brittany might call it an A, John Crary, who I know is on, might call it a B if you just ask them. But then if you show them both at the same time, their answers will converge differently, just kind of based on the gestalt. So I think Brittany's figure even probably showed it a little, the one with all like the triangles, circles, and the crazy Venn diagram or whatever. I think this is actually the biggest problem in machine learning. No one even agrees what you're supposed to be looking at, and no one agrees what you're supposed to call it. So with, I don't even get AI, just with kind of digital technology, you can do these, you have to gamify it or no one will actually do it. But we've done this in other domains where you show experts 1,000 images, because that's about as many as they'll do. 100 images are shared by everybody, and then 900 images are shared by a overlapping number of raters. And you basically just have to keep kind of generating this knowledge set to define what quote unquote truth is. Because again, I mean, I'm not a neuropathologist, I'm a psychiatrist, but no one agrees on anything anywhere in medicine, let alone in like a little blob of schmutz on a digital slide. So, and Brittany, you obviously have some ideas on.
I actually really love the question, and I agree that there's an element of having to, figure out what you're training the computer or the algorithm to detect in the supervised setting. But unsupervised is where you can learn a lot more and a lot of new things. So I've been thinking about this question myself, and it's the approach that I think could be really fruitful is to train an algorithm to do, a basic chord versus diffuse categorization. But then instead of relying just on that answer, look at your activation functions for your hidden layer nodes and do an unsupervised kind of cluster analysis, and then look to see where those small dense ones are falling and see if you can put a new name onto a cluster that falls out with those, and then start correlating that with the biology in the clinical settings.
Yeah, and this is why, yeah, like you said, you can do essentially unsupervised clustering. You just feed it blobs, right? And the blob detector will pull out hundreds of features that none of us probably understand very well. And then you basically, yeah, just see kind of how the universe expands, and then you feed in the ones that you labeled yourself and see, where they said, one thing I always say is everything's a snowflake eventually. So, I mean, you can reduce everything down. I mean, I look a lot more like, fortunately, my kids look a lot more like me than other people. But, if we're doing a clustering of my family, my daughter looks more like my wife and my son's like more like me, so it kind of depends on the question. Sorry, I leaned on something.
Great. And I don't know, you kind of maybe started on this next question in the chat box. And I think Dr. Duggar briefly touched on this in the presentation. What is the effect of images being downsampled or reduced bit depth on results? This favorably affects storage, but does it change interpretations of humans or ML? So I don't know if anybody wants to take this one. I think there's a lot of caveats, and
I just answered simply, it just depends on the question. If you're doing the thing that Brittany showed you, white matter versus gray matter, you could use a 0.5x, and that costs a megabyte of storage. I just realized I've scanned 80 terabytes of slides at our brain bank, and just copying all 80 terabytes from my one computer to my other computer takes like 2.5 weeks. So if I was going to do a study where I try white matter and down whatever, I would not want to copy 80 terabytes of data because it would take forever. I'd, try to make thumbnails or something like that. The real reason the 20x, 40x probably matters is probably if you're at the individual plaque level, which is say, I don't know, 50 pixels or 80 pixels at 20x, that would be 4 times that at 40x. And so maybe it matters. I actually like scanning everything. I like having as much data as I can, but I don't have to pay for it explicitly. So if someone said, am I $50,000 a year happier with 40x versus 10x or 20x? If I wasn't paying for it, I'd say, great, use 40x. If it came out of my salary, the answer would be the other one.
You'd want to run those experiments. Oh, Dr. Camelo-Piragua, please.
I was just going to say that it depends what the question is, right? Like I personally work more on the tumor side. So we're looking at single individual cells or nuclei contours, for example. So having something at 40x becomes very important, right? So it depends on the question that you're asking. And I think the other thing that is very important is that, you don't have to kind of acquire all the fields of view of a whole slide image. You can decide how many fields of view are necessary. But I think it's very, very important to include within your both training and validation data set is any common pitfalls, like any potential false positive, and those can include anything depending again on what the question is. Anything from, let's say, like fibrin, blood clots, artifacts that the slide may have, to like things like, I guess for the ADRC world, like other things that are just beta amyloid deposits, but it's not what you're focusing on. You're looking on the plaques rather than just any deposit at all. For example, I'm just giving an example out there. So including, for example, for me, the work I've done on brain tumors, including normal, quote unquote, normal brain or reactive brain, non-neoplastic is very important to make that distinction, because this is where the tricky part comes. So I think that's something to take into account and include those fields of view to prevent that we are biasing ourselves towards the question we want to answer and make our hypothesis like 1 versus 0.
I mean, think of it this way, our camera, I think I just bought a new phone. It has a 40 megapixel camera. Unless I'm printing out a picture of my cat at, 200 inches by 2000 inches or whatever that corresponds to. If I'm printing out a 5x8, I'm not gonna be able to see the difference anyway. So it depends on what the ultimate use case is. And this is actually a big problem in the field. I mean, it's one of my interests. Copying, moving, storing data when it's really big is slow and expensive, but at the same time, no one's going to go back and rescan their entire brain bank again at a different resolution, because that's also expensive, personnel wise and whatever. So,
well, that's why it's always, just like with any experimentation, right? You're gonna have variables. Just summarizing this, right? So understanding when those variables are going to affect your outcome. So running small pilot studies on this. So SCAN, obviously being well powered, understanding, and thank you, Dr. Camelo-Piragua, because it's going to depend on your question. Even though somebody might run it on plaques and say, oh, resolution doesn't matter, but resolution might matter for tangles, might matter for glial tau. So we have to be very mindful of this. I'm really glad that these questions are coming about, because this is where that whole concept of understanding what data you're training your system on. Are you training your system on 40x and then throw in the 5x, understand how that's going on? So really understanding, I saw that there's, to lump this in, the compression question is the same case, because we have to come, a lot of these slide scanning systems, we can have a 60% compression rate, 40%. How does that affect? These variables do need to be tested. We can't just, because what happens when we assume? Right? I'm not going to say it because this is being recorded, but we have to make sure that we're being diligent. But at the same time, you have an hour to chop down a tree. How long are you going to spend sharpening your axe?
Can I pitch in here as well? To answer a little bit about the downsampling, bit reduction, and resolution and compression, I think deep learning models tend to handle this better than conventional image analysis. And even like in QPath, that came up in the chat also. QPath has machine learning, but it's based on conventional image analysis feature extraction. And those kind of features that you can pull out of that are more sensitive to compression and technical artifact. And the deep learning models are a little bit more robust, but they also take a lot longer to train. So I think it's sort of a trade-off, but if a human can see it, the deep learning model can probably handle it given enough data.
So like as an example, so we basically took Brittany's model from her cases and ran it in Emory, and I didn't think it was going to work at all, and it ran really well. The biggest challenge we ran into is we scanned old slides and they were really faded. So even when I looked at them like with my human eyes, I was like, yeah, these are just faded. So I had to retrain the model a little bit, I guess we would say, but mostly because again, the slides just were completely faded. So it was a little bit different of a task. And then you just look, after we ran it and it was kind of we looked at it and go, oh, these are really old and they bleach. So we just, and then we retrained it or tuned it a little bit and it worked surprisingly well. So
and the other thing, David, was updating the code. So that's the other thing too, is just like with your iPhones, whatever, everything gets updated and then things can go haywire. So understanding version 8 versus version 10 can be a little bit different.
I don't even want to go into Docker and all this sort of stuff for make everyone log out now.
So it looks like we have another question. When working with whole slide images from multiple centers and scanners, how does difference in resolutions from different scanners contribute to deep learning models? How do they account for this? So I think somebody mentioned you have to retrain on all the different resolutions. I don't know if there's anything else to elaborate.
No, for anything across institutions, we just use the same mod. We'd use 20x basically. That seems to be, or 10x or whatever. When I was talking about training at different resolutions, I was talking about if we were trying to do a white matter, gray matter segmenter, I could either feed in 40x data, which is, 5 gigs, or I could feed in 1x data, which is 400 kilobytes or 400 whatever, 4 megs. And one model is going to take probably 30 seconds to run. The other one's probably going to take 300 minutes to run. And I'm probably going to get better results anyway on the lower resolution model, because white matter versus gray matter is, I'm not saying it's easy, but if I'm looking at a zoomed in field of view, I don't even know where I am half the time, right? So that's where I was talking about the resolution. Across institutions, pretty much I spend a more amount of time looking at this than I want to. Almost everybody is scanning at 20x at a minimum. Occasionally I've seen that they're not, but I wouldn't be able to compare, like, you know, if UC Davis gave me 1x and everybody else in the free world gave me 20x, I would just not use the UC Davis data. It's just not comparable. In terms of between scanner differences, there is some minor differences in pixel size between some of the scanners, even at 20x and stuff like that. But honestly, I've largely ignored it. Lee, I don't know if you've ever pretended it was, I would just put in a covariate for where it came from, as opposed to worrying about 0.0076 microns versus.
Yeah. Deep convolutional neural networks can learn scale invariance, and they often are, especially in things like, you know, detecting cars for self-driving vehicles and things like that. You have to be able to recognize the same thing, whether it's near or far. So they automatically learn scale invariance. So if you're in the deep CNN setting, a small difference in scanner resolution is not going to make a big deal.
But there are cases where the model wasn't scale invariant, and someone feeds you a 40x slide that you think is 20x and your results look like crap, because suddenly the model.
To learn it, you have to feed it data that represents the whole range. So if you want it to work well across institutions, you should train on data across institutions.
So a lot of this can be handled also during training by manipulating scales artificially. And so, you know, if you want to have a robust network, then, you know, it's a good practice to, you know, introduce distortions that you might expect to see, you know, in the wild. And that includes things like color variation and scale variability. You know, the differences between the objective powers, even the, you know, among a 20x or 40x, there are very small differences across scanners, but we usually are thinking about bigger problems and not thinking about that so much.
Yeah, I mean, honestly, we could argue, what if someone's optics are cleaner than someone else's? I mean, there's so much. The 20, we're just assuming 20x is good enough.
So I will also say it depends also on the question, but we have come across issues on having different images from different scanners, and we don't get the same result. So we first try, you know, with the set and see how, you know, accurate it is compared to our data. And if we see that it's not comparable, then definitely you have to include from that center, you know, let's say you're working with 3-5 different centers, include each of these centers for each category that you are asking in the training data. And that that usually, you know, improves your accuracy, and then move forward. And then again, within each training set from each center, you have to introduce the same kind of variables and modifications, like, I don't know, rotations or colors or whatever you're trying to do. So that definitely improves accuracy. And that's something that, you know, so we're talking here about research, but if eventually, and it will happen, that some of those AI algorithms will move into clinical practice, it's like any other, you know, thing in pathology. We're going to have to train. We're going to have to see that it works in our institution, in our data set, in our samples. So that's important.
Yeah, and that makes it an FDA nightmare.
Yeah, the pre-analytic variability, I think, is still the most profound problem. So, you know, differences in the color profiles between, you know, two scanner vendors, those are very systematic, and you can correct those well because they are systematic. But it's how the, you know, stains actually look and how the tissues are processed at the different labs that's really, I think, the biggest problem we face.
Yeah, I mean, it's just like someone might be heavy on the H and light on the E for some reason, or, you know, whatever. So it goes into that, you know, schmaltz of, is it the scanner that's really causing the difference, or is it the slicing protocol, the staining? They keep it in for 8 minutes, you know, Thomas's lab keeps it in for 9 minutes, you know, then everything's a little darker, blah, you know, so it goes into the noise essentially of the system. And this is actually one of my, I don't say pet peeves, but this is why having these big cross university or institution data sets is meaningful, because it's getting better, but you could read, I was joking with Brittany earlier, you can almost always get your data predicted very well with the machine learning model, and then it goes to heck when you oh, I just saw something about tiling. Most of the scanners that we use actually don't really tile per se. They're what do you call it, line scanners. Dealing with tiles is a pain, to be honest, because like if your object happens to be on a corner, your model has to have been smart enough to have dealt with the corner essentially. But tiling per se, in terms of like, having a halo where it's lighter in the middle and darker at the edge or whatever, if you're using a traditional slide scanner as opposed to like a microscope that with a traditional objective, that's less of it's not as much of an issue.
Output of algorithms can be tiled in weird ways, though. Let's say you're using a UNet model for segmentation at high resolution and trying to stitch those back together. So it can look funny, and you kind of have to adjust for that if you're trying to make a pretty picture.
And it also gets confusing too, because in most cases you're actually feeding in, I'll just say 256 by 256 pixels. So if your objects happen to be relatively small in relationship to that pixel size, then most of your objects aren't going to be near the corner anyway, so who cares? But if you're, if it's some giant Uber plaque that is more likely to be on a boundary, then you have to, futz around with that and either resample or be cleverer about that kind of stuff. So again, I would argue it's kind of task dependent.
I have a question actually for the group, just if you could all comment. So this is a really nice overview, and I think a little bit more in depth of a presentation than some of the other sessions, which I think is wonderful. But I just was wondering if you could all maybe offer your advice to people who maybe are just getting into the digital pathology world, and perhaps, this is their first time exploring machine learning. Just if you had any overall advice regarding the types of questions to ask when utilizing machine learning, just because there's so much to take into consideration for the pre-analytical component, and just kind of general advice.
I guess my advice would be, don't fall prey to the idea that machine learning is magic and can do magical things. If a human can't do it, you're likely not going to get the machine to do it very reliably, except in certain specific circumstances. So think about something that is frustrating and slow, and use machine learning to try to automate it rather than solving the answer of everything.
Yeah, my gestalt is try to automate things that are boring. So I used to use Lee wrote an amazing blob detector. It is not a nuclei detector until I figure out if it's actually a cell. We wrote a blob detector, right? And so if I told my grad student, I want you to count, there's 900,000 nuclei on one of our brain tumor slides. And if I said, terrible grad student, your job is to count the number of fat and thin cells manually, they would probably not stay in the lab. But if I came up with a computer algorithm to differentiate fat cells versus thin cells, I could feel fairly confident that I could get something that did a relatively good job fairly quickly. Then you go to like the stuff we're working about, Brittany, the Taoist as opposed to the Maoist, or the, fat or whatever, Taoist versus not Tangleless. I don't know. My brain's not good today. Like that is probably a harder problem, because you have all these gradations of you have more gradations, but I think that could eventually be automated, where it could do a classification. These are the 5 categories of brown schmutz that I want to category. And most of the time it'll do a good job.
I would say the pre-analytical is super important. That's the most important, and this is where you should spend the most time. Because if something goes wrong down the line, it's really hard. So it's like thinking of all possible variables, and let's say you have an entity, try to put as many different examples of that entity or that question in as many different variables with, crappy tissue, fantastic tissue, ischemic tissue, whatever, like different variables of the same question. So that's very, very important. So I would say spend a lot of time on the pre-analytical aspect.
Yeah, and there's a lot of like latent stuff that like Brittany knows. Oh, we changed antibody vendors in 2019 because something happened. So probably they look the same, but if no one in the universe knows that the UC Davis cohort switched antibodies at some point and they just feed me slides, there's no way I would know that intuitively. And so this is, again, this metadata, pre-analytical variability, regions, blah, 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 or, even if you slice it 5 instead of 4 microns, or, who knows, that kind of stuff is the unknown information that can kind of waste lots of people's time.
I would say, don't be afraid to try this stuff. The software has come a very long way, and you don't need to be an engineer or even to work with an engineer to try this, but, apply your common sense and, hold out some testing data just to see, how well the algorithm really is learning. And it can just be a few images.
Collaborate. Even think of Marvel Comic. She had the Avengers, right? As a huge team fighting for good. Form your machine learning team. If you're at an institution, reach out to other departments. You might have a computer engineering department, which will have students who need projects. Even if you're isolated, say at a smaller healthcare college or something, you might have smaller colleges around that have, like, think of a lot of big cities or whatnot. You'll have a lot of partnerships. Like, I'm even thinking with Dr. Gutman, you have Georgia Tech, right? Georgia Tech partnered with Emory. So you have to think creatively on this. There's resources. And a lot of healthcare, I just spent a whole Sunday learning about machine learning and healthcare data. A lot of healthcare systems are moving towards this way, so they want to put in resources. Jump on that train. Why reinvent the wheel when there's infrastructure there? And plus, you can train the next generation of persons. There's a lot of people wanting to get into this realm, but they need that subject matter expertise, which you think of, like myself, I don't know anything about machine learning when I started this, but I had a problem and I communicated that problem. Granted, it took a while. Dialogue takes time. It's not a quick email. You have to come to the table and each understand each other's jargon. So try to think about that. I think that's the best advice I have. And feel free to reach out to us. My name is here. You can probably find me on the web, although some things might be a little bit, so don't click on certain videos. Bad joke. But yeah, we're here. That's why we have these webinars too. There's a lot of other things in these webinars. NACC has some great resources. We have some great resources, the Alzheimer's Disease Center, Digital Pathology Working Group. So feel free to reach out and we'll try to put you in contact with the appropriate resources, or just try to steer you right in the right direction. Hopefully that helps. I know sometimes these things can get scary and you're just like, I just want to solve this problem, but we're here for you. There's your Oprah.
Dave put this in the chat, but I'm not sure it went to the whole group or just the panelists. But getting started, if you're just thinking about getting started, QPath is great. And we talked about it last month.
Well, that's great. Thank you all. That was quite informative. And I believe the channel to all of the recorded webinar sessions were posted in the chat at the beginning by Hannah. So if anyone wants to look into that to watch last session's QPath focused webinar, just to remind everyone. And I think we're just about out of time. So I just wanted to thank all of the wonderful panelists today. Thank you so much for taking the time to participate and offering all of your extensive and diverse expertise to the machine learning session today. And I also just wanted to give a special thanks to Hannah Rosentretter for helping to plan and coordinate everything for this series since the beginning. I think, as you said, we're over a year now, so we're still going strong. So thank you so much for all of your help with coordinating everything and getting everything planned and IT things going so smoothly. And just to wrap up, our next session will be the next session that is our co-sponsored ADRC Digital Path Working Group and NACC series is focused on general troubleshooting. And this session will provide an overview on general troubleshooting and digital pathology related to image acquisition, data extraction, image editing, and data sharing. This will be the main presentation given by Dr. Russ Huber, and it is February 14th at 11 a.m. Eastern time. So hope to see you all there, and thanks again. Have a great rest of your day.